In the previous video, we have learned about the vector space definition, like any vector space will be like a vector followed with the two operations, and scalar multiplication and addition operations will be there, and it will be satisfying such that the vector over addition will be in an abelian group. Then in case of scalar multiplication, distributivity property it should satisfy, and associativity, that is outer operation, in which we will be taking two scalar quantities which belongs to the real set and multiplying with the vector, which should give the same result, like one scalar quantity multiplied with a vector, then later multiplied with another scalar quantity. The neutral element with respect to the outer operation also it results in the same element of the vector. So these are some of the conditions which will be checking for a real valued vector space. Then followed with that, we discussed some examples also, like vector v is equal to set of n real numbers. So n is an element of natural number. It is a vector space with operations. It can be considered to be as a vector space with operations, addition and multiplication by scalar. So how the addition can be done? Two vectors will be taken that belongs to the real numbers, and set of n real numbers, and addition will be like x1, first vector added with the second vector, which is equal to x1 plus y1, etc. up to xn plus yn. So component wise addition it is being done. Vectors component wise addition it is being performed. Then multiplication by scalar is like lambda will be taken as a scalar quantity, which is an element of R, real number. X is an element of n real, set of n real numbers. Then lambda of that n real numbers set will be there, ranging from x1 to xn, will be equal to individual elements, lambda multiplied with the individual elements of the vector or this vector, lambda x1 etc. up to lambda xn. This is the case with a set of n real numbers. Then next is like a m by n set of m by n matrices containing real numbers, where m and n element of natural number n. So it is a vector space with addition taken as a plus b, where a and b are considered to be as the matrices of size m by n. So my addition will be like component wise addition will be there, that is row by row addition. So if a11 and b11 are the first column of first row, then respective rows column wise addition will be performed, and it is defined like this. Then multiplication by scalar is like lambda is a scalar quantity multiplied with any matrix A. It will result in this matrix in which lambda is multiplied to the individual elements of the matrix. So here if a notation is given like R m by n, if it is given means it indicates that set of m by n matrices containing real numbers. It is equivalent to writing the notation as R m n. So this is the case with the matrices. The next is a set of complex numbers. C indicates the complex numbers. So in this also addition will be like the standard definition of complex number addition, it will be followed. Multiplication also based on the scalar quantity that is taken will be multiplied with the complex number to result into another complex set. Now, if the column vector can be represented as Rn, Rn will be considered to be as a column vector. Another form of representation is Rn plus 1. where n indicates the number of columns, n indicates the number of rows followed by one column. Okay, so n plus 1. And if it is a row vector, you need to represent means it will be denoted as R1 plus n, which means that one row followed with n columns. So if the row vector is specified, then it will be written like this. If X is a row vector taken from the matrix, then it will be taken as X transpose. Okay, so usually X will be used to represent the column vector. If row vector is used, then we need to take it as X transpose, which shows the transpose of X. Now, one more topic that is here we need to concentrate is related to the subspaces. Subspaces. Okay. So if we are having a vector V, you are having a vector V, then you will be having a subspace that is represented as a U vector. So vector V, if it is defined like V comma, that is a set V comma plus comma dot, if it is defined like that, then you will be having a U, that is the subspace, which is having a U vector performed on, and its elements were performed on the different operations like the plus and multiplication. This is multiplication, okay, plus and multiplication. So we can say that U, it is a subset of V. U is a subset of V, and U will not be equal to null set. Okay, so subspace will be like a smaller space, a smaller set that is within the vector space. So it is a smaller set that is within the vector space. So for example, we can see if I am taking a set of real numbers, n set of real numbers, that is n, here I am taking it as 3. So the vector that will be considered as, if I take a vector as x, okay, if I am taking the vector as x, then you can get the you can get the elements of this x as x 0 minus x. So a vector is given like this. Okay, x vector x with elements x0 minus x, which means that we are having some 3 elements inside the vector. Okay, 3 elements inside the vector. So in order to check that whether this vector, it belongs to the vector space R3, what you need to do, it should satisfy some properties. Okay, the first one is like some scalar value. Some scalar value, if it is multiplied with the vector, so this scalar value, you can take the scalar value to be as lambda. Lambda, if multiplied with that vector, you will be getting it as what? Lambda A vector, which will be an element of the vector space R. R3. Okay, and second condition is like, if you are taking two vectors A and B, which belongs to the vector space R3, that is, which belongs to the vector space R3, then A plus B will also be an element of R3. Okay, so if you take any value if you take any two vectors from the vector space R3, then the addition of two vectors also belongs to the vector space R3. So if you are considering this example, okay, x vector you are taking and elements is like x0 minus x. First, what you need to check for the scalar multiplication. You need to check for the scalar multiplication. So if I am taking a scalar variable as c, if I am taking lambda is taken as c, then what is the matrix that will be formed after scalar multiplication? You will be getting cx followed with 0 and then minus of cx. Okay, so this is the matrix formed after scalar multiplication. So you can see that in the resulting matrix, first three elements are there. First one positive, second negative, and third one is second 0 and third one is negative. So it belongs to the vector space R3. Okay, it belongs to the vector space R3. The next condition is like you need to take the two vectors for the addition. Vector addition, you need to take the two vectors. So here one vector is there, that is x vector, and you can take one more vector, that is y vector, and you can take the element as y 0 minus y. So after performing the addition, that is x plus y, what is the result you will be getting? You will be getting a vector with x elements x plus y 0 and minus of x plus y. Okay, so here also you are getting three elements. First one is the positive, second 0, and the last one, third row will be like negative element. That also it belongs to the set of real numbers R3. Okay, so here we can say that since both these two conditions is satisfied, we can say that what the given vector x vector, it belongs to the, that is, it is the subspace of R3. Okay, subspace of R3. From the definition, this x vector will be taken as the U, that is the element of U, and R3 will be taken as the vector space V. Okay, so this is how you will be finding the subspace for any vector space. So next video we will be learning about the linear combination and linear independence.